Hi, Alex. How are you doing? Hi, everyone. I hope everyone's doing okay.
Hello.
Hi, Brian. Let me get my files open here for tonight. Please check out Canvas for Unit 7.
I was looking at the assignment right now, and it was saying that it was locked on the 4th.
Okay. Yeah, sorry about that. I must have been. That's my oversight. 1 second. Because when we migrate the course over on Canvas, okay. Yeah, I'll fix that right now. Available.
Yeah, it says it was due February 25th.
Yeah, I see it. When I turn it on, I forgot to change the due date. Let's see. Okay. Let's change it to Thursday. Okay. I'll go ahead and save that. And then let me double check the lab. I think I checked the lab and not the assignment. Let me fix the lab date too. Okay, yeah, that's correct. Everything's good. Okay. So yeah, I fixed the due date. Sorry about that. Okay, so we have about a minute left. Please check out the notes and the assignment. And let me open my LC3. Okay, so it's 6 o'clock. Welcome back to CIS11. Don't forget that you guys have a holiday tomorrow. It's Cesar Chavez Day. So you are not supposed to have any class in session. Our district observed a holiday. So tomorrow you will have that off. We will still have Thursday session. And so for now, I think we're going to go over Unit 7. So if you haven't downloaded the notes and the assignments, make sure you do that. And then I'll go into screen share. Do you have any questions before we start? No question. Okay. So in this week, we're going to touch on some programming regarding multiplication in our lab, and we're going to use mod. And then we are going to get a little bit in depth with trap and looking back at the pseudo instructions, some of the details that we got from the beginning. We're going to review the information and then expand on the concept. So this week in Unit 7 or Chapter 7 notes, It begins with talking about assembly and assembly language. We've been working with the simulator and the editor for LC3 for quite a while. Now, if you choose to use other assembly language, for example, Microsoft ASM, you will find that Microsoft ASM use C compiler. I know that ARM64, some version of it uses C compiler, but like NASM, it would have its own simulator. So you would find emulator and simulator that would be helping you with writing your program. If you have a Raspberry Pi, you can also learn ARM by using the emulator, installing with Raspberry Pi. So there's some tutorial available for that. So in this class, we mainly use LC3 and we correlate that with C or C++. And then, so when we look at the assembly program, we write it in LC3. And when we have the program assemble, after you have your program written, then you would assemble the program. And in that, the assembler is the program that turns symbols into the machine instructions. So all your labels, all your instructions, your opcode and operands becomes machine instructions. And when you assemble, you actually build that assembly program. And in this class, our architecture is ISA. And keep in mind that even though it's in the same umbrella, some processor would have specific symbols and instruction sets. So assembly is really pertaining to specific instructions that is designed or built into that processor, and also the symbols, how it's used. So before you approach assembly language, you should, or before you write your program, you should look at the documentation and the reference, so that way you can further understand its opcodes, how to use its labels, and you would see a lot of the similarity in different type of assembly program. For example, if you're looking at like RISC specific assembly programs, you're gonna find registers being used. Some have more or less instructions because those instructions are gonna correlate with the machine instructions that's built for that processor. So now when we take a look at this program, this is the example program from your presentation in your notes. So this program allows us to multiply the number by a 6, okay? So like what we've seen before, we had loaded a label here. And in this program, they originated at 3050, which is uncommon. Normally for LC3, we would start at text 3500, but we load the label 6 to register 1. We load the label number to register 2, and we clear register 3. So we initialize register 3 with the 0. And then you would have an inner loop. So with the loop, you've seen this before in your lab. We would use again as the label, or you can call it loop, whatever you like. But in this program, it uses again label. And this allows us to incorporate the looping. And in looping, we want to branch. So now here, we're gonna go ahead and add number to register 3, right? That's gonna be the location for the number. We're gonna add that to register 3. And then our register 3 originally is clear, so simply it's just gonna contain the location from number from register 2. Then we have another line when it adds R1 with a -1 decimal 1. Here, this is gonna be used for counting for the iteration. So as it loops, it's gonna count down, and then as long as it branch positive, it's gonna come back and and re-loop again and reprocess the instructions that are here. So now when it no longer branch positive, then it's going to go to the next part, okay, which is halt. So the program's going to stop. And notice in this one, what we're doing is we're doing it like one of the program that we done in the lab where we use a block word, one block word. So the value that you put here is going to be allocating the space for that particular label, okay? And then for the 6, we simply fills it with hex 6. So in this approach, you don't have to add a 6 to a register, a hex 6. You can also fill it with the hex 6. Now, in this way, what happens is we're not going to be able to go to the location for 6, right? Because 6 simply is containing a value. Okay, so you can also fill it with the value, or you can fill it with an address. And then our program would end. So here, this way, we are not really tying a lot of the things, the label 6 to a location like hex 3100 or an address that we've previously used. We can use the fill to initialize a value for that particular label. And this allows us to multiply. And as you know, when we multiply, we just keep adding continuously so many times for our program. So you can use this approach and also be able to produce the same output as what you would add the hex 6 to a register and add register to register. So in this program, it would contain instructions. We've seen instruction throughout. It also contains a pseudo op or your assembler directive, and that would allow the computer, the processor, to convert, right, your directive to the low machine level. And then you have the semicolon for the comment. Okay. So when you work with the program, LC3 doesn't mind white space between symbols, so and case sensitive is ignored. So unlike other programming language, you don't have to worry about case sensitive. So you can type it all in caps, you can have it lowercase. Normally, the common practice is to use capital letters. And anything with the semicolon is treated as a comment, and that will be ignored. Okay. So, yep.
So I remember fill and stringsy, but can you explain the BLKW?
So for this, it's called a block word. And then in lab 2, I believe we have covered that. So you can allocate a block, right? Your word size is 16 bits. So you can allocate a block word for a certain type of data. So in this case,
So kind of like an array?
Yes, or something larger. So earlier we had only used like a location which is 16-bit, right? Like hex 3100, where you would store an integer or a value. But if you need to store something larger, right? Like think about how in C++ you would have int and double and long, etc. But in LC3, since we don't really type it, we don't use data type, what we can do is we can specify the allocated space by using this or the address. So when you use an address, you have a 16-bit. When you use a block word, and depending on the value that you specify here, you will be able to allocate larger space to hold a certain value. Okay. Now with the number, since it's going to be multiplying, right? We load here, and I feel like this program is not really complete because there needs to be more added to this. but we suspect that number would hold a larger value, so we want to allocate a larger space for that particular label. Any other questions? Okay, so let's go to your assignment. So in the assignment, it tells you to look at the same program. We're gonna identify the instructions or the mnemonics for opcodes in the program. So you have a load, a direct load, LD, that's in the second line. Then you have the AND, that will be on the fourth line. We use that to clear. We have a branch positive. We have the halt. And with halt, that would use trap. And then, yeah, so we have load and add, branch positive, halt. And the labels that are used in the program would be your number. And then we have another label called 6. And for the inner loop, we would use again. So those are the 3 labels. And the reason why I chose this program is I want to show you that labels can be used in different ways. So you can see we previously used it with a memory address. When we fill that, now we can fill it with a value. And so far in the last couple of labs, we start using label with loops. Any questions with number 1A and B?
In the code,
Mhm.
are we multiplying a number that we like put in by 6, or
Mhm.
like, how does it work?
So when you check now, when you check for the output, you want to check at number. Yeah. So it's gonna subsequently allocate a block word after, because we originated at 3050. So what you can do is you can, now I feel like, so this program it is incomplete in that we should store a result, because when you load 6, that's the 6, and you take the number and you multiply it by 6. But you need to find out if your program produced the right result. So I feel like it's missing a third label where your result would be. Right, because in this it didn't even store out.
Yeah.
So yeah, so you still have to do an ST, right, to the result after you multiply here. So yeah, I feel like there's maybe a few lines are missing in this particular example, but that's the one that the publisher and the author used. So I wanted to kind of show you. So to answer your question, it is incomplete. And in order to check your output, you probably need to add a label, fill an address to that label, store the value out to that label, and so you can check. But yes, it's multiplying the number by 6.
So if we're adding R3 and R2, in R3 it's 0, right? So we're just adding the number to register 3.
Right.
But if we do R1 #-1, it's supposed to keep the iteration, but the number never changes, does it? For the number in R2 or in the number stored in R3, how are we multiplying it by 6?
Yeah, so but the loop is allowing you to multiply it by 6. So when you have here, add R3, R3, R2, which means that you take the number, right, and you add it to R3.
Yeah.
And when you keep adding, right, if you keep adding multiple times, so let's say if I am doing 3 times 6,
Mm-hmm.
right, what does that mean? I'm going to take 3 plus a 3 plus a 3 6 times, right?
Okay.
Yeah, so when you're looping and you're re-looping, you continuously adding that same value multiple times, and as you do it, you're going to count down the value, so at the end you're going to finish out, you know, the 6 rounds that you're adding that value that's stored in the number.
Yeah, so we're not multiplying the 6 and the number in one like thing, we're adding it 6
Right.
times.
And there's no multiplication instruction in
that's why
assembly. Yeah, so we only add. Remember what I said at the beginning? The computer only adds. So if you subtract, you add a negative value, right? When you multiply, you add multiple times.
So dividing would kind of be the same thing. So we're going to be
going
subtracting.
reverse when we use subtraction multiple times.
Gotcha.
Okay, so now you see it. Good. Any other questions? I see a chat comment. Jason said R2 should be the same since that number you are repeatedly adding. Yes. So now this question 1C is very easy. That will be R1, R2, and R3. Those are the 3 registers that's shown in the program. And then 2 comments, right? We saw multiple comments there, so you can identify 2 comments. So the comment starts with the semicolon. So you have clear R3 as 1 comment. The other comment is R1 keeps track of iteration. So mostly reviewed today, right? Kind of go back to what we've been using so far and covering that. Sorry.
Hey, Professor, so when it hits 0, does that
Mhm.
count as it not being positive anymore?
So yeah, so that means that any value that's not positive, so 0 and negative, right? So when it hits 0, it's gonna halt.
Okay.
It's gonna go to the next line. But as long as it's positive, it's gonna keep going.
No, because I was just thinking like if it starts at 6 and then you subtract 1, it put 5, no? Wouldn't it start at 5?
Yeah.
You see what I'm saying?
Because you already loaded, you already have the value in the register, right?
So it's still gonna add, right?
Right.
Oh, okay, I got you. Oh, but if it didn't add it yet and the iteration was before it, then you'd have to add 1, right?
That's correct.
Okay.
That is correct. So now in recursion, if you recall in the last lab, we did Fibonacci and we use iteration, but we represent n-1 as the previous value, right? And then n-2 is the value before n-1. So that is represented a little bit different. All this is an iteration approach. It's a loop approach to multiplication. So you keep adding the same value multiple times, so that way you would represent the addition as multiplication. Okay. So no, this would not how it would be for recursion. You just using the same value and you loop through it, but I keep adding it. Okay, any other questions? So you're gonna see some of this in the lab this week, okay? So to continue with the notes, going back to what we've seen before, where the format for LC3, you can have the label that will be optional. And then in the case where you saw that with again, right, we have a label, and then next to it, we would have opcode and operands, like we would do the add, and then R2, R3, R3, etc. And then you can add the comment. Now, opcodes are reserved symbols that would correspond to the instructions. And those are add and load, LDR, LDI, branch, etc. Now the operands can be your registers, your numbers, label, and we would use comma to separate them. I've seen assembly language that does not use comma for separator, right? When it uses register, you just put space. But in LC3, we use comma to separate your operands. What could be an operands? We touch on immediate value, which are numbers. You can have order and type corresponding to our instruction format. Sorry, I got drop off of Zoom there. Let me go back to screen share. Okay, so label, we need to place it at the beginning of the line, and you can use it on the same line with your instruction. Or in the past, we have used label on a separate line. Yeah, I got disconnected sometime in the evening. I get spotty internet connection. Okay, so we saw how that was used in the example program, like again, or in the past lab, you have used loop label. And then, so next to the label, you can, so you, because white space doesn't matter in LC3, you can tab it and then make it align so that way it's easier for you to read it, or other people to read it, so you can keep it cleaner, right? So we can use tab to kind of align everything. Okay, so we can have it at the beginning of the line. And so when it sees that, it would know that it would be a label. And we can use label with instruction. We can use label when we fill, right? And so for the comments, you can add the appropriate comments that would summarize or explain the functionality of that part of that section of your code. Okay. You can also use comment to separate parts of your program, like what you've seen in the example program. And I know that some of you already done this in C++ and other languages. And it simply is going to be ignored by the assembler. let's talk about directives. So earlier we mentioned that there are directives, and these are the pseudo operations. And they do not refer to operations executed by the program. It's used by assembler, and it looks like instruction, but opcode starts with dot. Right, so the directives start with the period or the dot, like origination address. Okay, dot N. Earlier, Ryan asked, what is BLKW with the N value? It would allocate the number of words for the storage. So if we do a BLKW1, that will be 1 word for the storage. If we do a BLK2, the BLKW2, that will be 2 words for our storage, and so on. So if you wanted to create an array of memory, you can change the value for N, right? And that will allocate the number of words, the N value of words for your storage. We also use .fill. And when you fill it with an address like hex 3100, it automatically allocate 1 word and initialize with the value N. Or in the last example, we saw that we fill it with a value like hex 6, right? And that doesn't necessarily mean that it is a location, it's just a value. And we use that value for multiplication. And then
So
since
whether that value is an address or just a value depends on whether you use LD or LDI.
And ST. Because when you use LD, LDI, ST, STI, those are for data, right? And when you use the arithmetic operations like add, right, those are for just for the calculation. So you're correct. If you have to use the appropriate instruction for the purpose of that value. Like if you wanted to move the data to a location, then you do LD, ST. But if you just fill it, it's simply just initializing that value for that particular label. So when you do a .fill, right, it's just gonna section 1 word, which is 16-bit, for that address. Okay, but when you do block word, you can change the end value to have more than 1 word. Earlier we saw 1, but what if we put 5, right? We're able to allocate 5 words for storage. And then you can use strings, and strings is null terminated. So that would allow you to use the end character string. And you saw this when we did days of the week, right? When we saw how Wednesday require the most characters. So when we fill that, we got to make sure that it's aligned accordingly. So that way it would have, you know, all the other day's character fill into that particular location, and it will output correct text or characters. So when you do a dot strings, you would allocate the number of characters plus 1. Okay, so if my string has 5 characters, it's going to do a 5 plus 1, which gives me 6 location. Okay, so each of the location is going to hold a character. Question? Okay. So the chart gives you a little bit more details, right? This it is specific for your pseudo operation, your directives. Then we have pseudo instructions. Okay. And we touched on this a long time ago, since the beginning of like lab, when we worked on lab 2. So you saw that we use halt in our example and in all our programs, right? So when it executes the halt, that will be equivalent to a trap with vector 25. So that would halt the execution, and it would show on the console that there's halt process, right? You've seen that before when after you run the program, right? You look at your console and it shows halt process execution. Then you have in for input, and that would be trap vector 23. Is that the same as system pause? Yes. For in, we would use register 0 always, and that would they call it pseudo instruction because it entails other instruction, right? So we would have trap vector 23, and that prompt, print the prompt on the console and read one character from the keyboard, and it's stored in register 0. For the out, we can output that onto console, so it write the character from the register 0 to the console. So in and out use register 0, get C also use register 0. Now the out use vector 21 with trap. The get C use trap vector 20, and puts uses trap vector 22. Make sure that you remember these. You will see them on quiz and final exam. So the difference between out and puts in that out display one character on console. Puts will display null terminated string on console. And in, out, get C, and put all use register 0. Okay, any question? Okay, so let me pause there, come back to the assignment. Refer to the below format and provide an example that contains all the components in assembly language: label, opcode, operands, and comment. And you can come up with your own. So here are some of my examples. So I can have, let me put it on one line so it's easy for you to see. So in the past, we use label like pause, neg, number, loop, right? So we can create one. So let's say if we do a pause, and we can do an add. Sorry. R1, R2, and R3, let's say. So that would contain all the components. We have a label, we have opcode, we have operands. Okay. And then we can just comment this. R1 is gonna store value from R2 plus R3, right? So if we need to put it all on one line, we can do that. Okay, sorry. I was just hearing a little bit of background noise. So any question with number 2? Okay, so let's work on number 3. For number 3, it tells you to refer to the below program and answer questions A through C. But this is pretty easy. We touched on this earlier. I changed up a few things on the program. So for question A, it asks you to describe the purposes of line 1 through 4. So on line 1, you have origination address at hex 3050. That's the start of your program. Okay. So what I'll do is I'll put line 1. Okay. On line 2, you're going to load register 1. You're going to load register 1 with label 3. And then line 3, you load register 2 with label number. Line 4, you clear register 3. So for future exam, you will be given code in LC3, and you need to know what those lines are to do, or, you know, one specific line, what is that doing? Okay. Then on line 5 of the program for number 3, you see that we have a comment. It shows the inner loop. So for question B, it asks you to describe the purpose of line 7 through 9. So I'm going to put line 7. On line 7, we're going to enter loop labeled again. And when we enter the loop, we would add register 3 with register 2 and store result in register 3, I'm sorry. So on line 7, we enter the loop labeled again. And as we enter the loop, we add register 3 with register 2 and store the result in register 3. For line 8, we are going to subtract 1, or we add negative decimal 1 to register 1 to reduce loop count. That's a decrement. So as you see in the comment, it keeps track of the iteration. Then on line 9, we would branch positive, branch if positive, it will reloop. Return to again label. Otherwise, it's going to exit or halt on line 10. Okay. I know it wasn't in the question, but okay. Any question with number 3? So we look through the program and we look at each line. So how does it know to check when it's looping? Look at this part right here. Okay. So if you start with a positive value, register 3 has number, which we can have it. Register 2 has number, and you would take number and you would put it onto register 3 by adding register 3. So here you have a 0 plus a number. So if let's say number stores a 7, right? So at that point, you would have a 7 initialized to the number location. And then when you subtract that with 1, right, it's still going to be positive, so it's going to keep looping. And then the next round, you subtract it again, it's going to keep looping until it gets to 0, then it's going to exit, to answer Lewis' question. So it keeps subtracting until it gets a non-positive value, then it goes to the next line. Any other questions? Okay, so for C, the purpose of line 13 through 14. So for 13, we have, we allocate 1 block word, which is 16-bit, for number label. Okay. Line 14, we have a label 3, so you declare the label 3, and it contains hex 3. And then after that, we just end the program. Okay, so for the project, make sure we know how to implement loop. There will be, I will talk about the project later, but there will be requirement or criteria where I would ask for specific technical thing, right? Like implementing loop, implementing stack, use appropriate label, use appropriate opcode and operands, and you would have correlated points for those areas. Okay. Any question with number 3? Okay, I'm going to move to the next page for number 4. Okay, so for 4, this one seemed familiar to you, right? This is a program that we had written a few weeks ago. So here we're going to look at the program and you're going to find the directives. Okay, those are the one with the dot in the front. So the first line, we have the origination address right here. That's 1, so .org. Then we have a bunch of strings. So we have dot strings near the end of the program. We also have dot fill, where we would fill for the characters, right? That will be A, so dot fill. We also have dot N. And I wanted to clarify this. So this is your directive, but this will be your pseudo operation. Actually, that's fine like it is. And then you also have other, right, pseudo instructions. So the first four we listed was pseudo operations. Then we have pseudo instructions, which is put, get C, and halt. Any questions so far? And if you look at this program, we talked about how it does the Ascii conversion with the offset 48, right? So when we subtracted the 16 here 3 times, that would allow us to Ascii convert. Give me 1 second. Never mind. Okay. Then next we're going to look at trap codes. Sorry. So we use the same program, right? Based on what we listed in the last one, okay? I'm going to relist them. So you have a put, you have get C. What else did I list? I forgot already. See a moment, halt. So if you look at your notes, okay, put uses vector 22, for trap, get C use 20, and halt use 25. So we can list that. So for halt, that will be vector 25. And then for get C, that will be vector 20 and puts vector 22. Okay, so those are the 3 that we see in the program. Any question? Okay, so now let's look in the notes. Okay, so you can find the trap information on page 3. And here are some style guidelines, right, which should go to the next question. So the style guidelines is that they suggest that you provide program header. Okay, so comment you wanted to put, remember at the beginning, I show you how you should comment. You can put your course number, the purpose of your program, and then the input, output, and side effects. Then you can start labels, opcode, operands, and comment. Make sure that we align it so that way we use column-like. Okay, for each line, we would use comment to explain the purpose. You would then give explanatory comment for most instructions. So we want to include comment in our instructions. You should use meaningful symbolic names, like how you would, so when you use identifier, think about how you would use that in your C++ program, right? So it's easily readable to you, right? Like ASCII to binary, input routine, save to register. You should section your code and include comments for the section. So provide comments between program sections. And your line must fit on the page. And I don't think we have issues with LC3 because it's pretty simple, right? We don't have a super lengthy line. Just be careful with no wraparound and truncations. So long statements, just make sure that you apply aesthetic with it. Okay. So you can take this information and put it for the next question, which I did. Okay. Okay, so for number 6, you can find the answer from the notes. Just look at the guideline section of your notes. And you will find it on page 4. So since last week, we have seen this diagram, right? So this is a flow chart for input characters and, or actually the looking at the occurrences, how frequent that character appears in a file. Okay. So when you start out with the program, remember that we talk about solving the problem, breaking it down to sub-processes, right? And here what we see in the flow chart is that it has the subtask as instruction, right? Like when you have count is going to be 0, so register 2 is going to represent count, and it's going to initialize at 0, so we just do a clear. Then if we have a pointer to the first character, so that pointer we can use register 3, and we need to tie register 3 with a location or an address. So that would be 3012. Then when you do an in, that simply is a trap, vector 23. When you do a load, character from file, right? So here register 1 is going to store that with register 3. Now, I feel like this is missing the conversion task. So between here and here, there gotta be ASCII conversion. Okay. And then after that, we're gonna go to where we would branch. Okay. You branch with loops, you branch for if-else statement. Okay. Now, if you do just a BR, you can send right, your program to a certain section, or you can do a jump. So unconditional branching, you can force it to go to that low label, or you can jump to that label. But in the case of yes, no here, that will be conditional branching. That's when you use 0, positive, negative. And when we do conditional branching, usually we apply subtraction. Okay. You can have addition of a negative value, or you can just simply do an addition and check that value, and you can branch for the condition. So here they did include the Ascii conversion, and Ascii conversion is for output. Okay, but we need to Ascii convert both times. Okay, so here illustrate the flow up of that program. And this is the program in LC3. When I taught Microsoft ASM before, one of the assignment that I gave was for the student to take input, like have a user type in their first name and their last name, and then swap it, like reverse it. So scramble the name and make it backwards. And it sounds very easy. It's easy in C++ and higher language, but when you look at LC3, you got to move it accordingly. You got to know where you place those characters so you can pull it for how you use the pointer to pull it for output. So if you want to practice in LC3, see if you can solve that, right? Take your first name input, then take each of the character, right? And then make it backwards, as your name backwards as an output. Okay. So here what you can see is you can see how that program is written. Okay, and in this one they use the LDR. And remember what I said about LDR is when you would use the immediate value. So we've been using LD and LDI with label, but when you do an LDR like this, you can use it with an immediate value, like a decimal or a hex. Okay, so when you do an LD, you use it with the label PTR. And then on this one, after we subtract, we branch 0, and that's going to go to the output. Okay. So as you can see, it's organized in different sections, so you know exactly what that section is supposed to do. So if you're not sure, read line by line and see what it's doing. Okay. And this one also is a fill with the offset. And then for the pointer, it just goes to the address, hex 4000. Sorry, my dog keeps wanting to go outside and then come back in. Lay down, buddy. Okay, any questions with this? Okay, so before we answer the next question, let's look at the next part of your notes. Okay, so you have used the simulator quite a bit so far, right? And if you look when you assemble your program, right, it's giving you different files. And you would use the OBJ file to simulate. Okay, so this is the process when you click assemble the code that you wrote. So in the first pass, it's going to scan the file and it's going to find all the labels and the corresponding addresses. So when you do a fill, it's going to take all of that information for the first pass. And it's going to put it into what's called a symbol table. Then next, it's going to look at your origination statement. That's the start of your program. That's going to be the location for your first instruction. So whenever you scroll down, you can jump back to the beginning by going into the origination address. And we have always been using hex 3000, right, thus far. Okay. Then after that, it's going to initialize location counter so that way it keeps track of all the subsequent instruction. And for every line that's included in your code, if the line contains the label, that label it's going to get added to the symbol table, and it's going to get added to the location counter. That's how it's able to find the location of your data. So when you do a fill, right, label 1 hex 3102, that address and that label name is going to go into the symbol table, and it's going to put it onto the location counter, the LC. And for all the subsequent instruction, after that, it's going to increment the LC. So it's just going to place it following. So by practice, we've been using label with the address like they are sequential, right? Like 3100, 3101, 3102. But because the process is that it's going to increment the location counter. It's just going to count +1, +1, +1 for all the subsequent. Okay. So what does that mean? When you use block word or strings, it's going to increment. So when we have a string, and if the string have 5 characters, it's going to start, let's say, at 3100, and it's going to do 3101, 02, 03, 04, 05, 5 location for 5 characters plus a null termination. So 06 is how it allocates for the string. Okay. So the note here, it says that if statement is a block word or a dot strings, if it's a block word or a string, it's going to increment LC by the number of words allocated. So if I do a block word 2, right, then it's going to increment 2 for the block for me. Okay, 2 location. And if I do if I have a 5 character strings, it's going to give me 6 location because there's a null terminator. And when it reaches .end statement, it's going to stop. So that's in the first pass. The second pass is when it's going to convert the instructions to the machine language, and it's going to refer to the symbol table. So it has to build the symbol table first before it convert the instructions, because the instructions is going to use the location that's declared, right, which is stored on the symbol table for execution. So for each executable assembly language statement, it would generate the corresponding machine language instructions in binary. And so when you look at your simulator, you see, right, like if we do .org origination address at hex 3000, right, you would see that in the binary. It would have the 3000 value. That's where it's going to start your first instruction. Now, if the operand is a label, it's going to look up the address from the symbol table. So when you do like an LDIR1 label 1, it's going to go to the symbol table to find, right, the address or the location for label 1. Okay, so it takes 2 passes to assemble your file. And it's going to give you the .asm, the .obj, a .bin, and a .hex. Okay. So in this case, when you're doing an inappropriate argument, right, it's going to throw an error. So when you do a not R1 and a decimal 7, that's not correct, right? We cannot do not R1 with 7. We can do a not R1 R1, okay? Because what we're trying to do is not 7 and put it on R1, it's not going to understand that. If you're missing a register for the destination or the operands for the source, then it's gonna not complete that instruction. So it's gonna throw an error. And then when you're trying to add a label with the register, it's also gonna tell you that it cannot do that. It doesn't understand what you're trying to say or trying to do. Okay. So it follows the format for what we've seen as what in the earlier pages. And each instruction would have specific format. So therefore, if you don't have it in the proper format or syntax, it's not going to work. Okay. We saw this problem before when we have arguments that are too large, right? Remember how you were trying to add hex for DE, right? It's larger than the 5 bits that's allocated for immediate value. What it tells you, it can't do it, right? Because if you're trying to put data that's larger than what it can handle, right, then we have overflow, and it's not going to be able to put that into the word size, that because there are only 5 bits in that word that's going to be handling the immediate value, the number that you give it. So be mindful of the number that you're using. So in this case, how do we handle this? We talked about this before. We would handle it with multiple line of codes, multiple instructions to add it, right? So we need to break it up into subpart and be able to add, so that way we would have a total add of 1023. Okay. So with the address associated with the label, there are more than 256 instructions. It can't use PC relative addressing mode. So just be careful with how you're using immediate value and how you're using your operands. Okay, so the answer for the next question is here. Okay, and you will see similar questions on the final and quiz. So when you assemble the program, the assembler, it's going to create, okay, from the assembler, we're going to have a .bin file that's going to hold binaries. We're going to have hex, that's going to be your hex listing. So it simply is the same file in different format, right? So here, that's going to give you the binary. This is going to be hex. This is going to be for the simulator. That's your object. The symbol table .sim, that's where your labels, your address, that's where it's going to store. And then listing file, that will be your LST. Okay. So for the next question, question 7, you always save your file for assembly language as a .asm. Whether it's Microsoft, NetASM, ARM, they're all ASM. When for LC3, when you assemble, you generate a .bin, a .hex, a .sim, a .list, a .object, OBJ. Those are the type of files here. okay, once you assemble the program. It's like building the program with, you know, your C++, right? When your IDE, some IDE calls it build, some IDE calls it run. But when you assemble your program, you create these files in LC3, and you would use the editor. To simulate, we would load the object file. Okay, so for question 7, it asks you for part B. It says what file is used to simulate the executable image. That will be your .obj. And then what is used to maintain your labels and your addresses. That is your .sim or symbol table. And then part D, it asks you what type of statements will increment the LC during the assemblies process. So you can go back to the notes here. Oops, let me put this. So when you use the .blk or .strings, that will increment your LC. So block word or .strings. Okay. So for question 8, it asks you to look at the statement and identify the problems for each statement. A, your immediate value is too large. Anything above 256 decimal, it cannot handle. So too large for A. For B, that's also too large, even though it's negative. And then for C, it's also too large. So how do I know? Okay. How do I know, right? If it's a decimal, anything above 256, if it's a hexadecimal, if it's more than 5 bits, right? Each hex value is already 4 bits. And in this one, I have 1, 2, 3, 4, 5, 6 hexadecimal digits. That means that it's a lot more than 5 bits. So it's definitely too large. And in this one, we should use fill. And also when we fill, we might have to fill it for multiple labels. Too large. Okay, so now you kind of see how you would troubleshoot your program and looking at directives, looking at your pseudo instructions. Okay, and now it's about styling because we already know the mechanics in assembly by this point. And assembly is not hard, it's very easy. It's just getting used to the format, the syntax. Okay. The computer is very simple at the lowest level. Okay. Now, before I answer now, I'm going to flip to the notes real quick so you know where to find that information. Or if you read the chapter, it also talks about it. Okay. So the object file format, the file contains starting address, right? The machine instructions. So here, what you see is the origination. That will be your first instruction. It's going to place it at hex 3000. Okay. So this line is going to tell it what to start, and then it's going to take this instruction and put it at 3000. Now it tells you here that an object file is not necessarily a complete program. You can have, so they consist of system provided library routines, code blocks written in by multiple developers. So for LC3, you would use the object files, and you can load multiple object files into memory and then execute at the desired address. So what does this mean? This means if you're familiar with Java packages, if you took my class, we spent a lot of time on it because I want to make sure you know how to use it. Or you're familiar with, creating modules for package in Python, right? So when you write package, you can have multiple programs, okay? And these programs would work together to give you modular approach in programming, or pieces of the program, and they work together, okay? So in LC3, we can do the same thing. You can write multiple programs, and then you would point for each of the program, right? You would point to a location or an address where you would start executing it. Okay, I've done this in Microsoft ASM. LC3 is a little limit in this area, and in our case, I don't think we would actually write it this way because I think it's already challenging for you enough in some of the more complex program that we're going to address in the next few labs. So I really care that you understand the very basic, like, I don't want fancy smancy thing from LC3. I want you to write a working program for your project, okay? The bells and whistle, you can add all of that later, okay? So it's important that you understand the basic mechanic of assembly, right? But in the later time, let's say that in your other classes in upper division, and you want to do a project, you can use modular approach, okay? Jason mentioned that we can recycle or reuse modules and reuse pieces of the program. So that way you don't have to rewrite it over and over again. Instead of a very large program, you can write, like, in Python, I would have my student create one module and we can reuse that module in other programs. Okay. And that's how a lot of the Python library works. Okay. So you often see that for assembly developer, they write these type of programs for libraries. Okay. So then you can utilize it for different purposes over and over again. So the important part to take away from this is to execute it, you need to tie it to an address, and you have to have that stored, right? It needs to really take that program and point to a location. Now, system subroutines such as keyboard input and that are loaded automatically loaded into the system at hex 3000. So often that we would start there, right? But when you look at other assembly language, they would require addresses too, and you can start in different ranges, okay? And some of the other assembly language, you would use this, like a 0. That's where you tell where the address is instead of just a hex. Okay. And then some of them use 00. So, and you can always refer to documentation for syntax. So the user code should be loaded between the beginning, right, and the end point. And so for LC3, the end point is FDFF. Okay. And your object file would include the starting address. So when it sees the .origination, it puts it on the symbol table, which object file uses that to. So if you delete the symbol table, guess what happened? Right? What happened to your program? Okay. And the last bullet point, this is be careful not to load overlapping object files. So you cannot overlap addresses. It will not work. So think about how you allocate your memory when you're using modular approach. Okay, so now you see there's option. Okay, so some of the few things that's important to also make note of assembly is that in the loading process, it is a process of copying executable image into the memory. So in the more sophisticated cases, you would see that it's able to relocate images to fit the available memory. Okay. Now, for the branch target, the load and store addresses, it has to be able to read those. Okay, because load and store is where our data is going to be. Branch is where it's going to find your section of your code. So in linking, it is a process of resolving symbol between independent object files. So if you learn Microsoft ASM, or if you use Microsoft ASM, you will have to link before you build your program. Otherwise, it would not work. So there are other assembly language that will require the linking process before, so that way it can resolve the symbol when it executes. Okay, so linking is a process of resolving symbol between independent object files. And also we can link libraries in assembly. And suppose we define the symbol in one module and want to use it in another, right? Like how we would have a library module and we want to use it in our program, we would have to link them. Okay. Now, like I said, in assembly language that use C compiler, right? Like if it can use like Visual Studio. So if you use Visual Studio, you have to set up the configuration option for linking. You have to point to which file you're linking to, and you have to set up the path. Okay. Otherwise, it's not going to be able to find the file. Or if you want to reduce the process, then you can, instead of setting up the path, right, in all packages, practice is that we put it in the same directory using the same name of your file, right? And this is what you see in Java, in Python, in C++. So, you know, if you're telling it that you're linking it, you have to tell it where it is. And that's important because they are independent of each other. Now, I've done with my class before, I've done where we point to the subsequent memory addresses, but you still have to link those files together. Otherwise, it doesn't know that they're supposed to go together. Okay, and then I've seen this all the time in other assembly language where you use a dot external. So when you use a dot external, you tell the assembler that the symbol is defined in another module. Okay. So we can say that, like if we're doing like label from another module, right? And reference like import. So when you import for Python, you do an import this from that particular module, right? Or you can say with this from, and Python interpreter would understand. So in the background, this is what's happening. It's doing an external. Okay. And the linker, it's going to look for the symbol table, and that's how it's able to find the symbol to resolve when you work with multiple modules or multiple files. Okay, so keep in mind that when you work with assembly, you are now doing a lot of the mechanical manual things that the compiler handles, right? So you have to be knowledgeable in this area so that way when you create multiple modules, you know how to handle that. Okay. So let's answer the last few questions, and then we're probably going to end up finishing early. So for number 9, right, using LC3 assembler, what type of files are generated for Windows system? Windows system, you use executable.exe. Microsoft uses MSI for installer, but it uses exe for executable. And we just touch on the tips when loading multiple object files in assembler. You should look at the last page of your notes. For question 11, describe loading and linking processes when using multiple LC3 object files. In loading, you're copying an executable image into the memory. In linking, you're resolving symbols between independent object files. They're different. Okay. So once you understand assembly concept, it's like how you learn C++, you can probably find the general concept in other languages very close to it. So you can understand most of it. Just the syntax is going to be different. Some of the use is going to be different. Like the instruction use is a little different, but this is why universities and schools teach LC3, because it's the easiest to learn, and once you got it, it's adaptable with other languages. Okay, questions? All right. So for 10, look at the last page and then find the answer and include that there. And then finish up with 11. Save your file. If you finish, if you want to submit it tonight, you can upload it on Canvas. Okay. So before the lab on Thursday, please take a look at it. It's a little longer than the last one. Okay, it has a lot of details. So think about how you would approach it, and then I'll walk you through the lab. Okay, now what I'm suggesting is even after you complete the lab and turn it in, you should go back and see if you can rewrite that program in LC3 on your own without looking at your notes and things like that to solve the problem that's asked. That's how you're going to get better, by practicing it. Okay, because some of you probably have forgotten some of the things we've done from the beginning labs, right? Because as you get more information, our brain is just going to flush out some of the temporary stuff, and it might just override it, right? So I suggest that you practice, and that's how you're going to understand. And if something that you didn't get, right, you can ask me, or you can go back, look at your notes, and you can reference your notes and your exercises, okay? So I suggest that's how you're going to get better, because when you get to, let's say, Cal State or UCR, right, in the case if you use this again, you would understand how to apply it, okay? So if you can explain it to another person how that program is, how you write it from scratch, how it's used, then at least you got the foundation for LC3. Okay. All right. So with that said, I think I'm finished. Any question for me relating our assignments?
Are we gonna have a midterm next week?
No. If you have taken my classes before, but you haven't, so I don't do midterms. I do quizzes and project and final. Yeah, midterm
Got it.
is, yeah, so there's only one true exam in the class, which is the final exam. And then I weight your grade on your quizzes. So don't worry about the midterm. So we have one more week before the spring break. And then when you come back from spring break, we'll talk about the project. Okay. Yeah. So if you have questions, you can message me. I'll stick around for a little bit and I'll stop recording if you don't want to be recorded when you ask questions. If you want to ask questions privately, you can come to my office hours. Sometimes if I'm not there yet, it's because I'm probably stuck in a meeting. Like sometimes they schedule overlapping meeting with my office hours, but just send me an email and then I'll drop off from the meeting. I'll come to the office hours, but I'm generally there. Like today I was there just doing other things, but I was on Zoom. So let me know if you have questions. If you want me to answer an email, you just write me. Type your name in the chat. You already know. Have a good night. I'll see you Thursday. And enjoy tomorrow off.
Good night.
Bye. See you Shabbos Day tomorrow. No school. Night.